Okay, so this is the question and numerically greatest term. So numerically greatest term means the value of the term is maximum, right? The
Yeah.
numerical value is the highest. So if you have some term tr plus 1 is equal to, in this case it will be 9cr, 3 to the power 9 minus r minus 2x to the power r. This is a term, right? This is the
Hmm.
general term, and tr is, tr would have been, I would have put, instead of r I will put r minus 1 everywhere. So it will be 3 power 9 minus r minus 1 minus 2x r minus 1, right? So let's say this term is the numerically greatest term. This term is numerically greatest. Then what we know is that uh, then what we know basically is that mod of tr plus 1 by tr is greater than equal to 1, because then only it is numerically greatest. No, mod has to be put because it is greatest. So the value of it has to be higher, right?
Yeah.
Tr plus 1 by the previous, basically this term by its previous term must be greater than 1, no, the ratio.
Correct.
So also you should have uh, tr plus 1 by tr plus 2 is also greater than 1, right?
Okay. Yeah. Right.
So it should be like the value of this term, this is tr minus 1, tr, this is tr, this is tr plus 1, and this should be tr plus 2, right? Then only this is numerically greatest.
Correct.
So these two inequalities have to be solved. If you look at your book, there will be a result that comes after solving these two inequalities. In general, you can say that in any in any series x plus y to the power n, tr plus 1 will be what? ncr x power n minus r y power r. Tr will be ncr minus 1 x power n minus r plus 1 y power r minus 1, and tr plus 2 will be ncr plus 1 x power n minus r minus 1 y power r plus 1. You have to get the inequalities mod of tr plus 1 greater than 1 and mod of tr plus 1 by tr plus 2 is greater than or equal to 1. Both of them are happening at the same time, then tr plus 1 is, then tr plus 1 is numerically greatest term. This is there in the theory, no? You've seen the book.
Yeah.
So this is fairly straightforward to understand also. It's not some difficult thing. Now you have to divide and solve and get inequalities.
Yeah. I'll do it.
If you divide this and this, you'll get some things. You'll get ncr by ncr minus 1, and this is 1 by x, and this is y is greater than equal to 1, and here you'll get ncr and ncr plus 1, and this will be x by y is greater than equal to 1. Now both the conditions have to be true, so you can simplify it a little more. Eventually, after simplifying and all, the condition that comes on r, it says solving both inequalities, you will get n plus 1 by 1 plus mod a by b n plus 1 by 1 plus mod a by b is less minus 1 is less than minus 1 is less than equal to r less than equal to n plus 1 by 1 plus mod a by b. After solving for r from this, you can divide these two relations to or multiply these two relations to cancel the x and y, right?
Right. Got it.
You will get, or you can leave it as it is and just put the values of x and y that are given in the question. For example, here in our question 3 minus 2x and stuff, right? So we know x is 3, y is 2x, and x is equal to 1 also. So y is minus 2. In our particular question, x is 3, y is minus 2, right?
Correct.
Put all of these things, you will get inequalities of n on n and r, and you just have to solve it. Finally, this is the result that he gets for any binomial theorem expression. A plus b is your x and y here in this. Here see a plus b was playing the role of x and y. This is in a plus b to the power n expansion. So a is my x and b is my y. So it is basically x by y only.
Yeah, got it.
Just have to read through what is being said in your theory book. You just read through it and it will come. Ultimately, it's just these two inequalities. You can solve the two questions that you have doubts on that. Other types of doubts, tell me.
No, there's no, the rest all was we already discussed, so I didn't face any problem in the remaining questions.
Okay. Uh, then we discussed 25C10 that question, no, till 10C10.
Yeah, the hockey stick thing.
Okay. And then we also discussed integration and differentiation basic stuff, right?
Mm,
Integration and differentiation to sum or series.
yes.
Some basic examples like C1 plus 2C2.
Yeah, yeah, we discussed three examples.
Okay. This one becomes n into 2 power n minus 1.
Yeah.
Then there are some more cases that we can see. We also did one example where C1 square plus 2C2 square plus 3C3 square and all, right?
Yeah, we did it.
C1 square plus 2C2 square plus 3C3 square. So here what was being done was, anyway, to get a square you have to take one time this and one time reverse, right?
Yeah, yeah, reverse.
And then to get 1 2 and all, you have to differentiate one of them, right?
Hmm. Hmm.
Differentiate one of them and then multiply after that. To differentiate, after differentiating once, this becomes n into 1 plus x to the power n minus 1, and the series becomes c1 plus 2c2x plus 3c3 x square and so on, right? And this side the series is x plus 1 to the power n is equal to c0 plus c1 x plus c2 x square plus no c1 x power c0 x n plus this series is x power n plus c1 x n minus 1 plus c2 x n minus 2 and so on plus cn x 0, right? So when you multiply this and this, you'll get x power n minus 1, right? And multiply this and this, you will still get x power n minus 1, correct? And this and the third one will be c3 x power n minus 3, right? This and this multiplication will be
Right.
x power n minus 1 again. So the coefficients of x power n minus 1 are coming out to be c1 square plus 2c2 square plus 3c3 square and so on. Is coefficient of x power n minus 1 in the expansion of n into 1 plus x to the power 2n minus 1. So that will be n into 2n minus 1 cn minus 1, right? That is what is supposed to be found. That is the answer of this series.
Yes.
Then let's look at some more examples. So first, let's look at this series. What is the sum of C0 plus C3 plus C6 plus C9 and so on till, like, obviously it could go till Cn. If n is equal C3n, you can go to, right?
Correct.
If n is a multiple of 3, it can go till there. If it is not a multiple of 3, then it will end at the previous multiple of 3, right?
Hmm.
Only the multiples of 3 are coming in the series.
Correct.
0, 3, 6, 9 and all. So try to think about how we can do this one. So if I'm writing it till 3n, then that means the top must be 3n or something, right? Otherwise, how will it be, right?
Correct. Correct. You told that last class.
If it is going up till t3n, then you are assuming that the top is 3n. So it is 3n. This is the series that I want to sum. So first thing you should write is 1 plus x to the power 3n should be what? It should be c0 plus c1x plus c2x square plus c3x plus c4x4 plus c5x5 plus c6x6 plus so on till c3n x3n. Now, how can we somehow remove the c1 and c2 terms, right? We have to remove those terms somehow. How will we try and remove those terms? Uh, so here, the idea is, which not many people will think of in the first instance, the idea is put x is equal to 1 first, right? So it becomes 2 power 3n is equal to c0 plus c1 plus c2 plus c3 plus c4 plus c5 plus c6 plus so on till c3n, right? So this is obvious.
Yeah.
Then put x is equal to omega. Omega is a cube root of unity.
Yeah.
Cube root of 1, complex cube root. So you'll get 1 plus omega to the power 3n is equal to c0 plus c1 omega plus c2 omega square plus c3. Omega cube is 1. c4 plus c4 omega plus c5 omega square. Omega power 4 is omega, omega power 5 is omega square, plus c6 is 1, and plus so on. c3n, right?
Correct.
Then put x is equal to omega square now. So it becomes 1 plus omega square to the power 3n, right? Is equal to c0 plus c1 omega square, right? And c2 omega power 4, right? Omega power 4 is going to be omega
Yeah.
plus c3 omega power 6, which is 1, plus c4 omega power 4 into 2 is 8, but omega power 6 comes out to be 1, so it is still omega square only, right? Plus omega power 5, 10, but it is 9 plus
Cor-
1, so it is omega plus c6 plus 1 c3n, right? If you now add it, If you now add it, what will happen is, see, C0, C0, C0 will become 3C0, but C1 will become C1 1 plus omega square, right? 1 plus omega square is equal to 0. This cancels. C2 also becomes 1 plus omega square cancels. Plus 3C3 plus C4 will cancel. C5 will cancel and C6 will come, right? Plus 3C3n will come. Are you understanding?
Yes, sir.
So that will be equal to now 2 power 3n plus 1 plus omega power 3n plus 1 plus omega square power 3n, right? Correct.
Yes.
So the answer of our series basically is C0 plus is equal to 1/3 of 2 power 3n plus 1 plus omega power 3n plus 1 plus omega square power 3n. And now we have to simplify this so that it is not complex. Actually, this is definitely a real number, so this should also come out to be a real number, right? Right.
Yes.
So
Yeah.
we have to simplify this part. So let's think about that. 1 by 3, 2 power 3n plus 1 plus omega power 3n plus 1 plus omega square power 3n. Write this 1 plus omega and 1 plus omega square somehow as, you could write it as cos theta and all, right? So you can say that 1 plus omega, I already know what it is, minus half plus root 3 by 2i, right? Correct. I know the value of omega. So this becomes half plus root 3 by 2i, and that is basically in polar form, that is equal to r, which is 2. R is 2 for this. No, 1 by 4 plus 3 by 4. So 1 for this. 1 cos of theta. Cos theta is equal to half, right? So that is 60 degree. So cos 60 degree, cos pi by 3 plus I sin pi by 3, right? Is it making sense?
Yes.
So 1 plus omega power 3n will be what? 1 into cos pi by 3 into 3n by De Moivre's theorem into sine pi by 3 into 3n is n pi, right? Correct? So cos n pi plus I sin n pi, right? And sin n pi becomes 0, so cos n pi, right? Correct.
Correct.
Cos n pi can either be 1 or minus 1 depending on whether n is even or odd, right? If n is even, cos n pi is 1. If n is odd, cos n pi is minus 1, right?
Correct.
Similarly, 1 plus omega square will become 1 plus minus half minus root 3 by 2i. So that becomes half minus root 3 by 2i, right? So this becomes, this can be written as tan theta is minus root 3, right? So you can say that it is going to be 120 degree, right? Tan 120 is minus root 3, right? So this is, r is again 1 cos 2 pi by 3 plus I sin 2 pi by 3. No, that is wrong. Uh, oh, it is correct only. Okay? No, no, this has to be negative. So,
So it should lie in the last quadrant.
so it should be 1 cos minus pi by 3, right?
Yeah, so we can write pi by 3 itself.
Minus pi by 3 we cannot write as,
No,
for this we
cos
can write
almost pi by 3.
plus I sine minus pi by 3. So this becomes basically cos pi by 3 minus I sine pi by 3, right?
Right,
Correct. So this power
right,
3n would be simply cos 3n into this. So cos n pi minus I sine n pi. So this is 0 anyway. So it is just 2 cos n pi, right? The sum of this and this.
correct.
So the answer is 2 power 3n plus 2 cos n pi 1 by 3, right? Correct. So that can be, if
Yeah,
n is odd, it will be 2 power 3n minus 2 by 3. If n is even, it will be 2 power 3n plus 2 by 3, right?
right,
So the idea here is that whenever there are three spacings, right, in between combinatorial coefficients, right, what we are basically doing is putting x is equal to 1 omega omega square, right, and adding. In that way, you will be able to eliminate the two which are not multiples of 3 from the middle. You understand?
yeah,
You will be able to eliminate C1 and C2 because those, after these three additions, those will have coefficients like 1 plus omega square, right? So let's try to solve some questions. Is C0 plus C4 plus C8 plus so on, right? Here there are multiples of 4, okay? Question 2 is C1 plus C4 plus C7 and so on. You have to find this, then there is C0 C1 plus C1 C2 plus C2 C3 and so on till Cn minus 1 Cn minus 1 Cn. uh, okay, then C0 plus C0 plus 3 C1 plus 5 C2, 3 C1 plus 5 C2 plus 7 C3 and so on till 2n plus 1 Cn. Okay, and the last question for now is find the sum of C0 plus C1, C1 plus C2, C2 plus C3. This is not a sum, this is a product now. Oh, hold on for a second. And the last one is Cn minus 1 plus Cn is equal to, you have to find this product, you have to find the last question. Try these five.
Yeah.
They should tell you many things. Okay, I'll be back in 5 minutes once.
In the first one, the same idea works. Same idea as 1 plus omega square, right?
Yeah.
So basically, what will you do? You should take fourth roots of 1. All the four complex roots of 1, what are they? 1 minus 1, I minus I, right?
Correct.
If you take all the four complex roots of 1, then you can say that when you put the values of those roots in the binomial theorem, right, there will be fourth power terms that will not be touched, right? That will always be 1, 1, 1, 1. Correct? In the sense that C0 plus C1x
Yeah.
plus C2x square plus C3x cube plus C4x power 4. So if you put fourth roots of 1 there for x, this term will be untouched, this term will be untouched, right? Correct.
Correct.
The remaining terms, when you add, what will happen is finally they will cancel off. No, sum of all the four roots will be 0.
Yeah, like the previous question.
So C1, C2, C3 will get cancelled. C4 and C0 are untouched. Eventually, you have to just find the sum on the right hand side, right? So it will be 2 power n, right? 2 power n plus 0 power n plus 1 plus I to the power n right? Plus 1 minus I to the power n, right? And 1/4 of that, correct? Makes sense.
Right.
Because 4 times 4 times will come, no? So
Yeah.
now you just have to simplify this, express it in the complex number polar form, and then similarly get the cos sign expression, right? Because this is always going to be real. So when you express this in polar form and all, you'll get cos sign expressions, right? You can say that this is basically r cos root 2 into cos 45 plus I sin 45, right? And this is root 2 into cos 45 minus I sin 45, right? Correct.
Correct.
So the sum of those two will be 2 power n by 2, 2 power n by 2, which is the power, and 2 times of that, cos of n pi by 4, right?
Yeah. Yeah.
And then you can take common and all, or and divide by 4 and stuff, right? After that, you will get the answer. That is the answer. Okay.
Yeah.
So this part is solved in the exact same way. So what it tells you is when there are missing coefficients and all, no, think of if there are 3 missing and there is a pattern 3 3 3 3 missing, right? Then it is always going to be using cube roots of unity. If there are 4 missing, then it will always be using fourth roots of unity, because sum of all 4 roots is 0, right? So you can use that condition to remove the unwanted terms, right?
Correct.
So similarly, C0 plus C5 plus C10 you could have done by doing fifth roots of unity, right? We will not be doing that case because it will be complicated calculations, but you could have done it in the same way, right? Question 2, 3, 4, 5, 2.
Just 2 minutes. Sir.
So try. I was just telling you this because it's the same idea. Try
Yeah.
these yourself. 2, 3, 4, 5.
Sir,
Second question, you guys could got it.
mm. So in the second one, we have to do the same thing we did in the previous one, like 1 plus omega square, right?
But slightly different, no?
Hmm?
Slightly different,
It
no?
will be slightly different because the terms are different.
So how
In
will
that,
you do that?
so basically in this we have to do
Because
is,
C1 is there, no?
yeah, C1 is there, correct.
So if you have C0 plus C1x plus so on is equal to 1 plus x to the power n, how can you get C1 term there, right? C1 term as the first term. So multiply by x square, right?
Correct. We can multiply by x square.
So it will become C1 x cube plus C2 x power 5, no, x power 4
4.
plus C3 x power 5 and C4 x power 6 and so on. And then put 1 omega omega square.
Yeah,
What will happen is C1 will stay, C4 will be there, and C7 will similarly be there. All the other ones will disappear. Right? So multiply
yeah,
by x square to shift the terms whenever needed. Right?
yeah,
Multiply by some power of x to shift the term. If you know the pattern that you need, then you can multiply to shift the terms, right?
correct. So I think I
So after
got the,
that, you can get it. Like after that, it's simplification
yeah,
just. It will be slightly different than that case, but
Yeah, the
not
answer is
hard.
a little different.
So you just have to do 2 power n into 1 plus omega power n into omega square plus 1 plus omega square power n into omega power 4 and 1 by 3 of that, right?
Yeah.
So simplify it using the polar form to get the cos expression and all, cos sign, whatever, right?
Yeah.
Okay, so that is fine. Third one,
Mm,
C0, C1 plus C1, C2 and stuff.
yeah.
Right.
Okay, so it is a product this time, product of two coefficients. So hopefully you should get these coefficients as coefficient of some common power of x, right? Some power of x, right?
Correct. So we can use the identity we learned. That NCR is equal to n by NCn minus r, right?
You
We'll get
can
the
use
same
that.
power.
You could use that. So Cn xn, I was thinking more like if you reverse it, becomes C0 xn plus C1 xn minus 1 plus C2 xn minus 2 and so on, right?
Yeah.
Cn x0. Now look at what is C0 C1, right? See, it is coming.
Okay. Yeah.
C0
Right. We're
C1 is
getting
coefficient of x minus n minus 1
correct.
and C1 C2 is also coefficient of the same power now. C2 C3 will also be same coefficient, right? Correct.
Correct.
So it is coefficient of x power n minus 1 in 1 plus x power 2n, right? Correct. This left hand side is x1 plus x power 2n, right?
Yes.
Right hand side, is there any other way to get x power n minus 1? You will not get it. X power n minus 1 you cannot multiply with anyone else, right?
Yeah, we won't get it.
You will only get through C0 C1 and you will get through C1 C2 and stuff, right? So this will just be, what is the answer of this? Suppose you have to find coefficient of x power n minus 1 in this, right? Why have I written 1 plus x power 2n? Because when this and this multiply, it becomes 1 plus x power 2n. What will be the answer? Tell me here.
Answer to the final question, or
Answer here, this one. Coefficient of x power n minus 1 in this.
it'll be
2n c n minus 1, no?
like that. I was calculating it. Yeah.
Right. Right. Correct.
I mean, whenever you have 1 plus x power n, coefficient of x power r is ncr.
Yeah.
X power r in this is equal to ncr, no?
Yeah.
So it is
Right.
x power n minus 1 and 2n. So 2n c n minus 1, right?
Correct.
So this tells you one thing, that if you have product of two at a time and all, no? See, earlier when we did the one derivation of C0 square plus C1 square and all, we did the same thing. right? And it came as 2ncn, right? You remember in the last class we had done this?
Yeah.
Yeah.
The same thing we had done, reversed it and multiplied and checked, right? There, the difference between the coefficients was what? Zero, no? Nothing. There was no difference. C0 into C0 it was, right?
Yeah.
So the answer was 2ncn, right? N minus 0, right? Here, the difference between the coefficients is what? 0 and 1 subscript difference is 1, right? Answer is 2ncn minus 1, correct?
Yeah.
So you can now generalize this result and say that C0, C2, for example, if I had to do, right? C1, C3, C2, C4, right? Correct. Cn minus 2 Cn, right? Suppose this was the question now. Are you seeing the pattern? Every time the difference is 2, right? Are you guys understanding? Don't mute yourself, guys. I cannot know what you're saying, no? Hello?
Yeah.
Don't
Yes,
mute
sir.
yourself. What is the point of muting?
I
I
was saying.
cannot, huh?
I was saying yes.
So don't mute yourself. You're muted.
Okay.
Uh, I don't know what you are saying. Then it is very weird for me to, yeah. So here the difference is 2. So then it becomes 2ncn minus 2.
Correct.
Why? Because you follow the same process, reverse it and multiply. You will notice that C0, C2 has power x1 minus 2. C1, C3 has power xn minus 2 again.
Yeah.
The same logic, it is coefficient of xn minus 2 in a 1 plus x power 2n, right?
Correct.
So that answer will become C2n cn minus 2, right?
Hmm.
So in general, what we can say now, generalize this, and we can say that if you have to take product of binomial coefficients where the difference between the subscript is r, right? And you have to take sum of all such two at a time products, right? Difference between the subscripts is going to be r. Like I will say C0 CR plus C1 CR plus 1 plus C2 CR plus 2, and this goes on till CR Cn minus r, right?
Correct.
Uh,
Yes.
no, wait, Cn minus r Cn. No, that is not correct. The last term.
It should be yeah, CN.
Cn minus r till Cn, right? This is the last term.
Yeah.
So this will be 2n Cn minus r.
Got it. Yeah.
Here it was 1 was the difference. When the difference was 0, it became 2n Cn, right?
Hmm.
So that is a general result, right? So the way we do it is write the sequence 1 plus x power n, then reverse it and choose the correct coefficient of x power, right? Which gives the thing that you want, right?
Right. Got it.
Okay. Fine. Question 3 is this, and we have seen some generalizations of 3. Then uh, then let's do question 4. I hope you are copying down what we are doing, right? You have
Yeah.
notes and all, no, for all
Yeah.
of
Yeah.
this. Okay. Okay, so question 4 now. Because I'm not sure if the Allen people will pay too much attention to this. They will just solve some examples and they will not bother much. Afterwards, it will become difficult. People struggle in this chapter when they are doing these types of summations and all, because for the first time it will be hard. It feels hard when you see it for the first time.
Right.
Hmm.
Uh, this one then, C0 plus 3C1 plus 5C2 and stuff. See, there is no missing term here, okay?
Yeah, I think uh, we did something similar last class as well.
That time it was a derivative type of thing,
Yeah,
but uh,
do something similar here, like multiply by x or something.
you could try that. Maybe it will work. So C0 plus C1 x plus C2 x square plus C3 x cube plus so on plus Cn xn is equal to 1 plus x to the power n.
Then we should multiply with x square. No, right?
Um,
No, that won't help.
if you multiply by x square, the other terms don't work out nicely.
Yeah, only the 3c1 term works out.
So it is not that. Here the general term, if you notice, all the terms are there, and TR is basically 2R plus 1 CR, right?
Correct.
And you have to do the summation of this, right?
Hmm.
Summation of R goes from 0 to n of 2R plus 1 CR, right? Correct.
Yeah.
So this can be split as summation of 2 times summation of RCR plus summation of CR, right?
Correct.
So RCR, I think we know how to do, because it goes from 0 to n, right? So RCR basically is 0C0, so C1 plus 2C2. This we have done earlier, right?
Yeah, this one we did 3c3 plus
4
4c4.
C4 and all. This is a direct derivative, right?
Hmm.
So this goes on till NCN, right? So
Right.
this series we know how to do. It is a direct, just take a differentiation. So that will become C1 plus 2C2x and so on. Put x is equal to 1, right? After
Hmm.
differentiating.
Hmm.
So this is basically n
Yeah.
into 2 power n minus 1, right? Right?
Yes, correct.
So this RCR is this. So 2 times of that is 2n into 2 power n minus 1. And summation of CR is what? From 0 to n. 2 power n.
Correct.
So this is just n into 2 power n plus 2 power n, right? So 2 power n into n plus 1, correct?
Hmm.
So this is fairly easy because you know parts of the summation, right?
Correct.
You can split it because you can write a general term in this way, and you can split it because you know RCR summation, you know CR summation, right?
Correct.
You could also have done this in this way. Let S is equal to C0 plus 3C1 plus 5C2 and so on till 2n plus 1 Cn. You could also write it in the reverse manner. 2n plus 1 Cn is equal to C0, right? Correct.
Yeah,
Because Cn is C0, that we know the property, no?
correct.
Terms from both ends, equidistant terms are equal, right? So
Correct.
the previous term would have been 2n minus 1 C1, right? The second last term, right?
Hmm.
and
Yes.
so on till C0 would have come one time, right? C0 would have come
Yeah.
if I reversed it, but I can write it Cn, right?
Correct.
I have reversed everything and now I'll add it. So 2 times S is equal to what? This becomes 2n plus 2 C0 plus this becomes what? 2n plus 2 again.
Yeah.
Everything becomes 2n plus 2, right? Correct.
Yes.
So 2s is equal to 2 times n plus 1 and summation of C0 to Cn is 2 power n. So S is equal to n plus 1 2 power n, right? Or the more natural thing to do is what we did earlier, this thing. This is a trick, like you would not have thought of this mostly, but this is a normal way to do it. Okay, write the general term and try to sum it, right?
Yeah, got it.
And we already have a no, we know this summation and this
Correct.
summation also we know, right? Okay, so last one is a product of these C0 plus C1, C1 plus C2 till Cn minus 1 plus Cn.
Now the last one.
So think about what this means. NC0 plus NC1, right? Multiplied by NC1 plus NC2, right? NC2 plus NC3 and so on. NCn minus 1 plus NCn, right?
Correct.
Now, this identity we had seen, what is the meaning of these are adjacent terms in one row of a Pascal triangle, right?
Yeah,
So the answer will be the bottom term. No,
correct.
Oh yeah, correct.
these are adjacent terms in Pascal's triangle, right? Because n is same on both, right?
Yeah,
So these two terms sum is the bottom term.
yeah,
That becomes n plus 1 C1, right?
yes,
Make sure that you understand that. So if you start from NC0
Yeah.
NC1, this is n plus 1 C0, right?
yeah,
And this is n plus 1 C1, right?
yeah,
NC0, NC1. NC1 plus NC2 will become what? N plus 1 C2, right?
Yes.
This identity we had seen last class.
Yeah.
That the sum of two consecutive adjacent same row terms is going to be n plus 1 C of the higher power subscript, right? Higher subscript. So the whole series can be boiled down to this n plus 1 C3 and so on till n plus 1 Cn, right? Correct.
Yeah.
Yes.
Okay. So now you have to simplify it a little bit, I think. N plus 1 C1, n plus 1 C2 till n plus 1 Cn. So actually this was a proof type of question where you have to prove that this is equal to C0, C1, C2, Cn minus 1 into n plus 1 to the power n by n factorial. Okay, so we have to prove that this is equal to C0, C1, C2 till Cn minus 1 into n plus 1 to the power n by n factorial. Okay. So now it is obvious how to prove it, because here all the terms were n, right? So you have to convert this n plus 1 and all and get your n, right?
Correct.
How many factors are there? N factors are there, right? So you can write this as n plus 1 factorial by bottom is 1 factorial n factorial, then n plus 1 factorial by 2 factorial n minus 1 factorial, and so on till n plus 1 factorial by n factorial and 1 factorial, right?
Correct.
From each of the top factorials, you can take n plus 1, n plus 1 common, right? It becomes n plus 1 whole power n, right? Into n factorial by 1 factorial, and right now it is n factorial, and n factorial by 2 factorial and n minus 1 factorial, right? Something like this, right?
Correct.
Till n factorial by n factorial and 1 factorial, right?
Yeah.
So what you can do is, okay, from each of those terms, right, in the denominator take 1 factorial, write it as itself, but 2 factorial you can write as 2 into 1 factorial, right?
Right.
3 factorial you can write as 3 into 2 factorial, right?
Yes.
4 factorial as 4 into 3 factorial, right? And lastly you can write n factorial as n into n minus 1 factorial, right? Correct.
Correct.
So what will come out? The take the 1, 2, 3, 4, those things till n common outside, right? So that will give you n plus 1 power n by n factorial in the denominator. Correct.
Yeah.
And then you have reduced each of these factorial terms by 1, right? This 2 factorial becomes a 1 factorial, this n factorial becomes n minus 1 factorial, right?
Correct. Correct.
Are you understanding? I am just
Yeah.
setting it up so that I will get this right now. Because
Mm-hmm.
1 factorial and this becomes 0 factorial and n factorial, right? Which is nc0. This becomes, because if it was 1 factorial, this would have been nc1, right? nc2 and so on till ncn, n minus 1, because this is n minus 1 now, right? Are you understanding?
Yes.
So what am I doing? I'm trying to prove this, no? So eventually I have to take this common and this common, right? I have just taken them.
Right.
Yeah.
You
Yeah.
will immediately get this.
Got it.
The main thing was to convert it into this form. After that, it was not very hard. Main thing was writing this one. Okay, which comes by using the Pascal's triangle. Makes sense?
Yes, I got it.
Yeah.
Okay. Then the next one is, one second. Uh, Find the sum of, okay, the series is C1 by C naught, C1 by C naught plus 2C2 by C1 plus 2C2 by C1 plus 3C3 by C2 and so on till NCN by NCN minus 1 plus NCN by Cn minus 1. Find the sum of this. So in questions where it becomes slightly complicated, always write your TR, okay? Like when it looks complicated, at least try to write your TR and then think, can I do the summation in some way, right? So here TR is easily written, at least, right?
Right.
What is your TR? Tell me.
Correct.
It is on top is C, same matching, right? So R CR by
R
C
C R divided by C R minus,
R
yeah.
minus 1.
CR minus 1, right?
Yeah.
And this
Correct.
R has to go from 0 to, no, R
Hmm.
goes from 1 to N,
Hmm.
right?
Hmm.
So basically we have to do summation R is equal to 1 to N RCR by CR minus 1, right?
Correct.
So since we don't know how to handle these fractions and all, so it's better if we try to simplify what is NCR by NCR minus 1, right?
Hmm.
That will be n factorial by n minus r factorial by n factorial by n minus r plus 1 factorial r minus 1 factorial, right? So n factorial cancels, this cancels and becomes n minus
Correct.
r plus 1 on top divided by r, right? This is what is coming.
Yeah.
So r into that is very easy now, right?
Yeah.
R into CR by CR minus 1 becomes simply n minus r plus 1.
Yeah.
Summation of this is super easy. Summation of r from 1 to n of n minus r plus 1, right? So that will become n into n minus n into n plus 1 by 2 plus n, right?
Correct.
N square minus n square by 2. So n square by 2 minus n by 2 plus n. So plus n by 2. That is equal to
Correct.
n into n plus 1 by 2.
Got it.
Correct. So this is n into n plus 1 by 2. Uh, See, here there was no very obvious binomial theorem series that could have given you this, right? It was just a normal summation where you take your general term and try to figure out if there is a way to simplify it, right?
Correct.
You took your TR and then try to simplify it and see if it works, right? So you are seeing that there are many different ways to approach these binomial sums. It is more of an art rather than like a standard method. Like you have to look at the question, try different things. Eventually, hopefully, you'll be able to figure out, right?
Hmm.
Okay. Then, uh, question 7. Let's look at. Uh, let's take this series 2 into C0 plus 2 square C1 by 2, 2 square C1 by 2 plus 2 cube C2 2 by 3, 2 cube C2 by 3 plus 2 power 4 C3 by 4, 2 power 4 C3 by 4 plus so on till 2 power n plus 1 Cn by n plus 1. Try this yourself. I'm sure you guys will be able to figure it out. Try to see everything that we have learned so far and try to apply it. Okay.
Yeah.
So,
Mm. Try it. Any ideas?
We have to write the R term and do the summation like we did previously.
Uh-huh.
Sir, we should use integration for this, right?
Yeah, we should use integration
Oh,
Okay, then I guess I almost got it. Just a minute.
because the denominators are nice patterns and all. See, if I had given
Yes.
you this series, right, then this one we had discussed. This one we had discussed in that last class when we saw okay, how to do a basic integration to get this.
Yeah.
Till Cn xn, right? So if you integrate this, it will become C0x plus C1 x square by 2 plus C2 x cube by 3 and so on, so on. Cn xn plus 1 by n plus 1, right? However, we want to integrate under limit so that we don't have that integration constant, right? Correct. So integration limit should be 0 to 1.
Yeah.
So this side also you have to integrate. So this will give you this series, right? Correct. So 0 to
Yes.
1, when you
Yes.
put, you get C0 by 1, right?
Yeah.
C1 by 2. So this is an obvious integration. So this will come. So the answer of this was 1 plus x to the power n plus 1 by n plus 1 and 1 evaluated from 0 to 1. So this was okay. So let's just keep it like that. But the problem here is that there is a 2 here and there is a 2 square here and stuff, right? Right. That is the issue. But the two powers are
Yeah.
going up from 1 to n plus 1, right? Correct. So what you
Correct.
can do is take 2 common, right? And this is 2 power 0 C0 plus 2 power 1 C1 by 2, right? Till 2 square C2 by 3, right? So on till
Yeah.
2 power n Cn by n plus 1, right? Right? Correct.
Correct.
Now, if you integrate from 0 to 2, now what happens? See? Wait 1 second. Oh, you don't have to take 2 common also, right? You don't even need to take 2
Yeah.
common actually. If you integrate from 0 to 2,
Yeah.
what
Yeah.
happens?
Yeah. Yeah.
2C0 plus 2 square by 2C1, right? Plus 2 cube by 3C2, right? That's it, right?
Correct.
Actually, you don't need to take 2 common. Don't take 2 common. Just keep it like this and see that if you integrate from instead of 0 to 1, you do 0 to 2.
Hmm.
You understand?
Yes, sir.
0 to 2, if you do, this becomes basically 3 power n plus 1 by n plus 1 minus 1 by n plus 1, right? So answer is 3 power n plus 1 minus 1 by n plus 1. Is it making sense?
Yes, sir.
Uh, is there any other way to do it also? Can we think of some other way also? If, for example, you didn't think of integration, you can write the general term and think if something comes from there, right? So
yeah,
let's
what of that?
so let's see, integration idea is obvious because this pattern you should know. This pattern. This is a standard thing that you should know. Okay. So it's not like the integration idea was not obvious. That you should have thought of. And from there, Just to handle the two powers, think of changing the limits a little bit, right? 0 to 2 instead of 0 to 1, right? So the answer comes, this is the correct answer. Let's try, however, a different way to do it also. So the general term was what? 2 power r plus 1 cr by, what was here? R plus 1, right? Correct, no?
Correct.
And the summation was going from where to where? R was going from 0 to n, right?
Correct.
R is equal to 0 to n, 2 power r plus 1 cr by r plus 1, right? So we have to try to simplify this part a little bit. NCR by R plus 1. Can we simplify it in some nice way? Hmm, okay. Let's write it a little bit. N factorial by R factorial, N minus R factorial, and R plus 1, right? And there is a 2 power R plus 1, correct? So the denominator is becoming actually n factorial by r plus 1 factorial, right? And n minus
Yes,
r factorial, right?
correct.
And if you add these two, it sums up to n plus 1, right?
Right, right.
Correct? So in a binomial coefficient, if it was n plus 1 factorial on top, I could have written it as n plus 1 c r plus 1, right? If there was n plus 1 factorial on top, right?
Yeah.
But there is n factorial on top, right? So
Correct.
I'll multiply and divide by n plus 1.
Yeah, we can do that.
Yes.
So this becomes this thing only, no, this thing.
Yeah.
And there is a 2 power r plus 1 also, right?
Hmm.
Correct. Now
Correct.
this is not very hard because you have to sum it. Let's write some, see, this is a constant term, right? Because r
Correct.
is changing. So 1 by n plus 1 comes outside, right? Summation is
True.
r is 0 to n, 2 power r plus 1, n plus 1 c r plus 1, right?
Yeah.
This is fairly
Yeah.
straightforward because this is, uh,
Yeah, I was
let's
getting
write
to the
a few,
answer. This.
so let's write a few terms here. It is 2 power 1 n plus 1 c1 plus 2 power 2 n plus 1 c2, right? And so on till 2 power n plus 1 n plus 1 c n plus 1, right? There is one term missing, and otherwise it would have been a complete series, right? The one term missing is r is equal to 2 power 0 n plus 1 c0, right? Correct.
Yeah.
If you had added that, then c is going from where? 0 to n plus 1, right?
Correct.
Correct.
So if you take the series 1 plus x to the power n plus 1, the terms will start from n plus 1 c0 till n plus 1 c n plus 1, right?
Yep.
Correct. And
Yeah.
in this series, see, notice that the power of 2 is matching the coefficient, right?
Yeah.
Power of 2 is always matching the combinatorial coefficient subscript, right? So that means x should be 2, right?
Correct.
If x is 2, then the second term will have an x, no, x here, right? Power 1, right? And this has power n plus 1, right?
Yeah.
This is the real series, right? So if you put x is equal to 2, it will become, this whole part is what you need, right? See?
Correct.
So basically 3 power n plus 1 minus n plus 1 c0, right?
Hmm.
Which is 3 power n plus 1 minus 1. is this part. This summation is 3 power n plus 1 minus
Correct.
1
Correct.
divided by n plus 1.
Yeah.
Okay, so both the ways you can do it. Integration is also simple only. This is also nice. Uh, but you have to first transform it in this way. You have to write it and then figure out that you can write it like this.
Yeah,
Unless
I
you,
didn't think of integration at the first thought, so then I did this way.
okay, uh, fine. So this is done. Then the next thing is, for example, let's do this one. N minus 1 whole square C1, n minus 1 whole square C1 plus, 1 second. N minus 1 whole square C1 plus n minus 3 whole square C3 and so on, all the odd ones. C3, n minus 5 whole square C5 and so on, sum of this till the last odd one. You have to prove that the sum of this is equal to n into n plus 1, n into n plus 1 into 2 power n minus 3. Prove.
Yeah,
This is fairly straightforward. I'm sure both of you should be able to get this. But maybe not very straightforward, but write the general term, then you'll get the idea, right?
yeah, just
Everyone is following these steps.
so. What if we write n minus r whole square cr as the general term that will include 2 as well, right?
What to?
Like if we put r is equal to 2.
Uh, yeah, that is a mistake. Ah, okay, that is not correct then, right? So it has to
Yeah,
be only odd numbers.
correct.
So has to be only odd numbers. Uh, Hmm. So we'll have to change it a little bit. We'll have to write it as 2k minus 1, right?
Correct.
2k minus 1 or 2k plus 1, whatever, right?
Yeah, both of them would work.
N minus 2k plus 1. K is varying, okay? Uh, okay, no. 2k minus 1, correct.
It has to be minus one. If it's plus one, then we get the different thing.
N minus 2k minus 1 whole square, ck. K goes from, no, C of 2k minus 1, right?
Hmm, hmm.
K goes from now from 1 to n.
Yeah, now I think it's fine.
So
Right.
n C 2k minus 1. Okay, fine. So the series will become n square summation of k from 1 to n, n C 2k minus 1 minus 2n summation of 2k minus 1 into n C 2k minus 1 from k is 1 to n plus 2k minus 1 whole square summation of, or summation of is outside, C 2k minus 1, right?
Correct.
Okay. Oh, okay. So here the first summation is not hard. The
Yeah,
first one is easy, right?
yeah,
Because it's just the odd ones, right? So it
correct.
is 2 power n minus 1, right? N square into this part will just be all the odd ones. So that will be 2 power n minus 1, right?
Hmm.
The second one and third one might be more complicated. So we have to think about it. Uh, Second one is 1C1 plus 3C3 and 5C5 and so on, right? Correct.
Hmm.
Correct.
Okay. Uh, if your last term was, let's say, C2k, then the last term would be 2k minus 1 C2k minus 1, right? If your series was still 2k, this would have been the thing, right?
Hmm.
Okay, so why don't we,
Yes.
let's say this is equal to s, and let's invert it. No, s is
Yeah, we
equal
could
to
do that.
2k minus 1 c, 2k minus 1 can be written as 1, and the previous one will be 2k minus 3 c3, right?
Hmm.
And this will be 1 c 2k minus 1, right? Correct.
Hmm.
Makes sense. The
Yeah.
inverting will be correct, yeah.
Yeah.
And then add it, 2s is equal to, this becomes 2k, and c1 everything is 2k, so c1 plus c3 again, so 2 power n minus 1, right? S is equal to k into 2 power n minus 1, right?
Correct.
And uh, wait, k should not have been there, no? So k is, this summation was from k is equal to 1 to n. Oh, last term was not k, no, it was n, no? What am I doing?
All right.
Right? Last term is not
Right,
k,
right,
right? It
right.
has to be
Yeah.
n, right? So this is going to be 2n, right? N into 2n minus 1, right?
Yeah.
This is the summation of this part, right?
Hmm.
Minus 2n into n into 2n minus 1, right? Correct, right?
Right.
I feel like I made a mistake, but let's see. The last one is odd squares, right? Odd squares. 1 square C1 plus 3 square C3 and so on. Hmm. Hmm. Odd squares, how will we do? So first we need to know how to do this, right? First you need to know how to do this. Then only you can say, okay, how I need to do only the odd terms out of this, right?
Yes.
You understand what this is? This is 0 square, 0 is 0. So 0 square plus 1 square C1 plus 2 square C2 plus 3 square C3 and so on, right? N square Cn, correct?
Correct.
Correct.
Okay. Then how will I get this? Let's think about it. 1 square, 2 square and all is there. Try to think. I'll be back in 1 minute, right?
Yeah.
Okay. Yeah, so we have C0 plus C1x plus C2x square plus Cnxn is equal to 1 plus x power n. Okay. And we have to keep, we know how to do C1 plus C2, 2C2 plus 3C3, right? That we know. That is a simple derivation, right? You know C1 plus
Yeah, yeah.
2C2x plus C3x square and so on, right? That is equal to plus NCN, that is equal to n into 2 power n minus 1, right? I mean, just C1, when you put x is equal to 1, right?
Correct.
So that was basically n into 1 plus x to the power n minus 1, right? But how right now we need one more 2, right? Correct. Oh, okay, I got it. I need one more 2, right? I need 2 square, I need 3 square and so on, right?
Correct.
Right now you have this much, no? This much you know, right? So
Yes.
how can you get another 2 into it, right? Or another 3 here, another n here, right? What I should do is multiply this by x and then differentiate again. Basically repeat the process. See, if I multiply by x, what happens? This will
Yeah.
come.
Yeah.
And then again, if you differentiate, what will come? Right?
Correct.
Basically, once you differentiated it, then you got 1, 2, right? 1, 2 comes from the top, from the coefficient after differentiating, right? Correct.
Yeah. Yeah.
The x square term gave a 2C2. And then multiply by x again, make it an x square term again, and then again differentiate, right? That will give you 2 square C2, right?
Yes.
Aditya, are you understanding?
Yeah. Got it.
So here differentiation would be n into differentiation of first term is 1 and 1 plus x power n minus 1 plus n into x into n minus 1, 1 plus x power n minus 2, right?
Correct.
And now put x is equal to 1 in this one. That will give you the c1 plus 2 square c2 till here series, right? So summation of r square cr is equal to n into 2 power n minus 1 plus n into n minus 1 into 2 power n minus 2, right?
Right.
So this
Yes.
take n into 2 power n minus 2 common, it becomes 2 plus n minus 1, right?
Yeah.
It becomes is equal to n into n plus 1 2 power n minus 2, right?
Yeah.
Right.
Correct. So that is equal to this thing, right? Now the idea is that we need to get the sum of all the odd numbers only, odd ones only out of this.
Correct.
I mean, I'm hoping that it is half of that, like, but not necessary.
It's not. We're not sure about that.
Yeah, yeah. How will you get just the odd powers? Just the odd powers if I want in this series. Oh, okay. Oh, then I have to just do what? This was my series, right?
Hmm.
I have to put 1 and minus 1.
If we put 1 and minus 1, then
If you put minus 1, what happens? Yeah, yeah. If you put minus 1, all the odd powers will become negative, right?
correct. Also, we can. Yeah, got it. Yeah.
And then add it, right? Or add or
Correct.
subtract, whatever works,
Yeah, yeah.
Anything.
right? In
Yeah.
this expression that we have, put 1 and minus 1, see what is coming, right?
Yeah.
And then add and subtract accordingly
Yeah.
to get only the terms with the even coefficients, right? Even coefficients have the 3 square c3, right?
Correct.
So even powers of x are having uh, the right thing that we need, right? 1 square c1 and 3 square c3 and stuff, right?
Hmm.
So you have to just put x is equal to 1 and minus 1 and add, right? In this expression.
Yeah.
Correct. Okay, so now we can solve it. Now actually the way to do the previous one is also clear, right? To just do the odd powers, don't do it like that method. Don't do that summation thing. Okay.
Hmm.
What was the what was the thing that we needed, right? We needed we needed minus 2 nr cr with only the odd ones, right?
Yeah.
We needed just the odd ones. So yeah, yeah. So correct, no, this makes sense, right? Just the odd powers we need.
Yeah.
Correct. So minus 2n is common, and this is summation of rcr with just the odd powers, right?
Correct.
So cool. So we know how to do summation of rcr, right? Whole thing, the whole thing we know how to do, right? Basically, it was c1 plus 2c2 x plus 3c3 x square, right? Plus
Yeah.
ncn x power n minus 1 is equal to n into 1 plus x to the power 2 and n minus 1, right?
Yeah.
After one
Correct.
differentiation, right? Correct.
Yeah.
Put minus 1 here, c1 minus 2 c2x. Instead of x, put minus x, right?
Correct.
Right? All the odd powers of x will be vanishing, right? When you add it later, right?
Hmm.
Instead of x, we are putting minus x, right? Correct.
Yeah.
So then when you add
Correct.
it,
Correct.
this and this will vanish, and all the even odd powers will vanish, or subtract it to get only the odd powers. Oh, actually, because we need this and this, we have to cancel these two, right? C1 and 3, C3 we need, no? Right? We have to just add it, okay? You understand? Finally, you need C1 plus 3C3 plus terms like that, right? You don't need the 2C2, 4C4 terms.
Yeah, we don't.
So add these two. So you get 2 times C1 plus 3C3 x square plus whatever, 5C5 x power 4 and so on, right?
Yeah.
Will be equal to n into 1 plus x power n minus 1 plus n into 1 minus x power n minus 1, right? And put x is equal to 1 here. You get n into 2 power n minus 1 plus n
Yes.
into 0, right?
Oh yeah.
By 2, right?
Yeah, by 2, yeah.
N into 2 power n minus 2 is that part, but you have to multiply by minus 2n also, right?
Yeah.
Correct.
And basically now you can solve the whole thing, right?
Yeah, now it's
First part was n square into 2n minus 1, right?
correct.
This part is this, and last part we have just done in the previous page, right?
Hmm.
Are you understanding?
Yeah, understood.
Okay, so look at your book, look at the series that are there, all the binomial series questions, right?
Yeah.
Try as many as you can, basically. Uh, Try all of the series questions. There is still one topic left, which we will do next class, and that is the multinomial theorem and all.
Hmm.
But chapter is more or less over if you are comfortable with the series type of questions. You have to attempt as many as possible.
Yeah, and then we can ask doubts next class.
Yeah. So you have to be comfortable with the series type of questions. Those are the toughest ones in this chapter. There's nothing very hard otherwise.
Hmm.
Okay.
Right.
So whatever we have learned today in the class, no, many different cases we have seen. Okay. So more or less it covers every type that you will encounter. Okay. So make sure that you go through your notes of today's class and last class properly.
Yeah.
Okay. That's it for now then. Okay.
Thank you, sir.
Bye.
Thank you, sir.